And with this, welcome aboard, Paul. It's your turn now. Thank you for being with us.
Okay, can everybody hear me okay?
Yes. Yes.
Excellent. Okay, thank you, Melinda, for this introduction. In the next hour or so, I will talk about soil salinity in Nevada. And as the title suggests, I will talk about what causes salinity, what effect does salinity have on plants and soils, and how can you potentially deal with salinity. And so what I will talk about is, first of all, why do soils become saline? How does it affect plants and soils? Then also, how do you determine whether or not you have a salinity problem? And then finally, how do you, if you do have to deal with saline soils, what are your options to remediate that? And I have to apologize in advance to those of you who have bad memories about chemistry classes in school. I will have to talk a little bit about chemistry because it's almost impossible to talk about soil salinity without bringing in some chemistry, but bear with me, and hopefully it will help you kind of understand what's going on when we talk about saline soils. And so, first of all, what I wanted to mention is that soil salinity is a problem that's it's truly a global problem and also a local problem. And so, according to the Food and Agriculture Organization, about 20% of the area that's being irrigated is affected by soil salinity. So 1/5 of the irrigated agricultural area is impacted by salinity. So that's a large area, and in Western Nevada, approximately 60% of the area of the land surface is considered saline, and some of those areas include playas. But when you exclude those playas, then still 40% of Western Nevada soils are affected by soil salinity. So it's an important problem, and it's an issue that's not going to go away. And in fact, it's expected to increase in the future. And as a side note, on December 5th, it was World Soil Day, and the theme of this year's World Soil Day was halt soil salinization. So it's recognized as a global problem, and as mentioned, it's clearly a local problem as well. So first of all, why do soils become saline? And in most cases, saline soils are present in relatively dry areas. There are some exceptions, but by and large, most of the soils that are affected by salinity are present in very dry area. And so there's a couple of reasons for that. So the main reason is why we have dry areas is that the amount of water that's leaving the soil through evapotranspiration, or that's leaving the soil from the surface, essentially exceeds the amount of water that's coming in through precipitation. So when you look at the water flow in soils in dry area compared to wet areas, so in areas that are relatively wet, so where if the water loss from the surface through evapotranspiration is smaller than the amount that falls on the precipitation, the net water flow into the soil is downward into the soil profile. So any materials that accumulate in the soil tend to get moved down in the soil profile. However, in arid areas such as Nevada, the amount of water leaving the surface of the soil typically on an annual basis is larger than the amount that enters the soil through rainfall. And as a result, there's a net water flow in the soil that's upwards. So it's going from the bottom up towards the surface. And so any materials that are present in water deeper in the soil are being transported towards the surface of the soil, which causes over time potential accumulation of salts. The other aspect that I will show in the next slide is also that most of the soils that are affected by soil salinity are present in relatively low parts of the landscape. And so to understand that, I made this admittedly poorly drawn diagram, but hopefully it will kind of explain what's going what's happening on the landscape scale. So here you have an area where you have a mountain range and a lower valley, which, you know, most of Nevada is essentially looking like this. So what's happening in a situation like this is that you have water falling on the land surface through precipitation. And then on the higher areas, this water moves down into the soil profile and starts moving down slope, especially if it hits a layer of low permeabilities, such as bare rocks or a soil layer that's that's not very conducive to water. And so, as a result of that, any materials that are present here in this top part of the landscape are being moved down towards the valleys and start to accumulate here. So ions such as calcium, sodium, potassium that are present in the soil and sometimes in the rocks are being moved down towards these lower areas. So you have an accumulation of salts in these lower areas. And then as water starts to evaporate from the soil surface, these salts are being brought to the surface and start to accumulate in the soil over time. And so you can also have higher up, sometimes you might find saline seeps where water kind of moves out of the surface here and starts to accumulate here. And so, but the main point that I wanted to make is that because of this landscape, the way that the landscape is made up here in Nevada is that materials that accumulate higher up are being transported down to the valleys where then these salts start to accumulate. And in our part of the world, you know, most of this particularly happens during spring when you have snow in the higher parts, and during snowmelt events in the spring, you have large amounts of water that move through the soil here, transported down to these lower valleys, and then with that water flow, these salts start to accumulate in these lower areas. And so what does it look like? There's a lot of evidence that you can see of salt accumulation on the landscape. And so this is an example here of an agricultural field where you can see this white material right at the soil surface. And this is kind of a dead giveaway that you are dealing with salinity problems, because this white material, it's all salt that accumulates at the soil surface. And you can also see what makes it sometimes even more challenging is that this pattern can be relatively spotty. So you see an area here that's completely white, and then some areas here that are not so white, and then here are smaller white areas. So it's not always evenly distributed across the landscape. And so, and this can be a main problem for crop production, as you see here, and I'll talk about that in a little bit more detail later on. This is an example of kind of a natural situation, and I mean, this almost looks like when I woke up this morning when, you know, we had snow here in Reno, but this is not snow, this is salt. And this is an image from the Great Salt Lake near Salt Lake City, where, you know, this is kind of an extreme example of where you have salinity, or you have salt moving to the surface. And this is primarily a natural process in this case. But you know, it's really illustrates what can happen when you're dealing with these extreme salt accumulations on the landscape. And then here are some other examples of what you might see. So here's some fields where again you can see this whitish material at the soil surface here and here, indicating that you're dealing with salt accumulations. And here's an example of what you actually might see at home. Sometimes if you have if you're growing plants inside, then sometimes what you can see at the surface of your pots is this whitish powder, which also indicates that you have salt accumulation on the surface on your house plants. Okay, so sometimes there's a little bit of a misunderstanding that, you know, soil salinity is always caused by anthropogenic effects, but in many situations, soil salinization is a natural process, again related to climate, but also landscape position. However, there are human impacts that can exacerbate this problem, and some of those are shown here, whereby so there are reasons why our actions can actually contribute to the problems of soil salinity. And one of the main problems, or one important problem that can happen, is that groundwater that's sometimes being used for irrigation can contain substantial amounts of salt. And so what happens if this groundwater is being pumped to the surface, water is being added to the surface, but with that water, the salt present in that water is being added to the soil as well. And so that can provide an additional input of salt to the soil surface, or to the soil closer to the surface area. Then also, if you have channels that transport water, if those leak, then water that contains salts that's being transported can move towards the soil, and those salts will be added to the soil. Over irrigation can contribute to salt inputs. And so there are some of processes that we do that can contribute to increased inputs of salts to the soil. And so as this water that contains salt is being added to the soil, because of these high evapotranspiration rates, water can move up to the soil surface again and leave behind the salts that have been added through our actions. Okay, so what I wanted to do next is talk a little bit about some definitions related to soil salinity, because soil salinity it's kind of a catch-all name for a specific set of problems and a specific set of conditions. So I wanted to kind of define what soil salinity means and talk about some specific problems associated with saline soils. So when we talk about a saline soil, we basically talk about a soil that contains large amounts of soluble salts. And what I mean by that is that these salts, such as kitchen salt, which is sodium chloride, when you put it in water, it starts to dissolve, and then the sodium chloride falls apart in sodium, which has a positive charge, and chlorine ions, which has a negative charge. And so, and there's many other salts that can be present in the soil. So there's sodium salts, calcium salt, magnesium salt, and then some of the ions that are associated with that are chlorine, as mentioned, but also sulfates, bicarbonate, carbonate, and nitrate. So these are all ions that can be present in the soil as salts. And so when we try to determine whether or not a soil is saline, what we do is measure. We take some soil. We saturate the soil with water, then we extract the water from the soil, and then we measure the electric conductivity of the water. And so water conducts electricity really well. And so one example of that is maybe as a kid, or even still, you're being told, well, never throw a hairdryer in a bathtub because you might get a major shock. And the reason for that to happen is that water is a very good conductor of electricity. And as you add more salt to water, this conductivity starts to increase. So when you know the conductivity of the water, you can relate that to the salt content of the water. So it's relatively easy to measure the soil salinity by taking a water extract, measuring the conductivity. And so as more salts are present, the conductivity goes up. And so when we think about saline soils, we measure the conductivity of a soil. And if this conductivity exceeds 4 decisiemens per meter, or sometimes you see different units such as millimoles per centimeter, if it exceeds this value of 4, we consider a soil to be saline. And I'll talk about this in a little bit more detail later when we talk about specific measurements of soil salinity. Okay, so that's for total, when we talk about the total amount of salts present in the soil. There is a very specific situation, however, that some people may have heard about, and that's when we talk about sodic soils. And so sodic soil sodicity is kind of a special case of soil salinity. And when we talk about sodic soils, we not necessarily talk about the total amounts of salts that are present in the soil, but we talk about the contribution of sodium to the total amount of salts that are present in the soil. So if I go back to this previous slide, I mentioned that when you talk about salts that are present in the soil, it can be a variety of such as sodium, calcium, and magnesium. But if a relatively large proportion of the total proportion of salts in the soil is occupied by sodium, then we refer to those situations as a soil being sodic. And so rather than focusing on the total conductivity of the soil solution or of the soil extract, when we talk about soil sodicity, we talk about the relative proportion of sodium. And we use two indices of soil sodicity, and I'll explain in a little bit in more detail how we measure this. And so there's two indices of soil sodicity that we use. One is the exchangeable sodium percentage, and the other is the sodium adsorption ratio. And again, I'll explain what these mean in a little bit. And so, but we assign values to each of these measures as a way to determine whether or not a soil is considered sodic or not. So when the exchangeable sodium percentage exceeds 15%, so an easy way of saying that if 15% of the salts that are present in the soil is made up of sodium, then we consider a soil to be sodic. And the sodium adsorption ratio, which is a related measure, if that value exceeds 13, then we also consider a soil to be sodic. Okay, so that's a lot of information, but I'll explain. Hopefully this will become clear in a little bit what I mean by exchangeable sodium percentage and sodium adsorption ratio. So this is kind of where some of the chemistry starts to get in. And so in order to understand particularly what soil sodicity means and how it affects soils, we kind of have to go back all the way to the basics and look at what and it has to do with how clay minerals are made up and what clay minerals do to the soil, particularly to the soil structure. So this image here shows an electron microscopy image of clay minerals. And I want you to focus particularly on these left two images here. So this is an image of what clays look like in the soil. And so you can see here the scale is about 0.5 micrometer, and 1 micrometer is a millionth of or 10 to the minus 6 meters. So it's a tiny fraction, but so it's a huge magnification here. But what you hopefully see is that when you zoom in on these clay minerals, you see that these clay minerals, they look like little plates that are stacked together in larger units. And that's particularly clear here, where you can see these individual plates that are kind of held together. And you can see the same happening here, where you have these platey, flaky materials that are kind of clumped together in larger units. And so when you start to look at the properties of these clay minerals, you can see the following. And so if you start to zoom in, so here again, you have one of those packages of these clay plates. And if you magnify that out, what you'll see is the following. So each plate that's shown here carries a certain charge, in this case, a negative charge. So you can, so a way to look at it is that each clay plate essentially functions as a little magnet that carries a negative charge. And I won't go into the details why this negative charge occurs, but it's a charge that's associated with most, that occurs in most clay minerals, and is permanent. And so because of this negative charge, what tends to happen is that you have positively charged ions, such as calcium, potassium, hydrogen, and aluminum. So ions that are kind of floating around in the solution, in the soil solution surrounding these clay minerals, they are being attracted to these negatively charged clay surfaces. So you can kind of get an accumulation of these what we refer to as cations, or positively charged ions, close to these clay surfaces. And this is important to understand, or important to remember when I start talking about what happens when we are dealing with sodic soil. So again, remember, clay minerals are negatively charged. As a result, they have this cloud of positively charged cations surrounding these clay minerals. Okay, so then we zoom in a little bit more, and I'll talk about two situations comparing a non-sodic soil with a sodic soil. And so again, here we have a negatively charged clay mineral that's surrounded by positively charged cations. So we've got calcium ions, we've got potassium, magnesium, and sodium in this case. So the total amount of negative charge associated with a clay mineral is also referred to as the cation exchange capacity. So basically, it is a measure of the total amount of these positively charged ions that can surround clay minerals. And so when you add up all this negative charge, in this case, it's 20 centimoles. Don't worry about the units too much, but you got 20 units of charge associated with this clay mineral. And that total amount of negative charge is then balanced by these positively charged cations. And so in this case, you have one atom of the sodium associated with this, that's present here in the solution here. And so one charge out of 20 of these potential charges is occupied by sodium. And so remember that I was talking about this exchangeable sodium percentage. So in this case, the exchangeable sodium percentage, or the amount of charge that's occupied by sodium, is 1 out of 20 potential charges, and that's equal to 5%. So the exchangeable sodium percentage in this case is 5%. Then let's go to the bottom situation here. So again, you have a clay mineral that has this, that has 20 units of negative charge, and it has all these cations surrounding this negative charge. In this case, this situation, however, you have much more sodium ions surrounding this clay mineral compared to the top situation here. So in this situation here, you have 6 out of a total of 20 charges that are occupied by sodium. And so 6 divided by 20 is 30%. So in this case, the exchangeable sodium percentage is 30. And so remember, earlier I mentioned that the cutoff for determining whether or not a soil is sodic or not is 15. So in the top here, you have a situation where the exchangeable sodium percentage is 5. But here at the bottom, the exchangeable sodium percentage is 30, which exceeds 15. So in this case, you're dealing with a sodic soil. And so going back to those indices of soil sodicity that I was talking about earlier. So here you have the exchangeable sodium percentage, which is the amount of exchangeable sodium that's present divided by the cation exchange capacity, or the total amount of negative charge that's present in the soil. And then you multiply that by 100 to get to a percent. Then the sodium adsorption ratio is a somewhat related measure, but the way that you measure that is where you take a soil, you saturate it with water, then you shake it, you extract the water from the soil, and you measure the sodium concentration of the ions, or the sodium concentration in that solution, as well as the calcium and the magnesium concentration. And then you use this formula where the sodium concentration divided by the root of the calcium and plus magnesium concentration. And that gives you the sodium adsorption ratio. So both measures are somewhat related, but from a numerical standpoint, they give you slightly different values. But you see both being used as a way to indicate whether or not you're dealing with a sodic soil or not. Okay, so the reason for going into this in a little bit more detail is that when we talk about soil salinity, you may end up dealing with very different situation. So you may deal with saline soils, you may deal with sodic soils, or you may deal with saline sodic soils. And so here I indicated the four potential situations that you may encounter in your soils. Here, this ECE represents this conductivity measurement, which represents the total salinity level. Then here, this represents the sodium adsorption ratio, and here the exchangeable sodium percentage. So these last two represent those measures that you use to determine whether or not the soil is sodic or not. So you may end up dealing with one of four situations. So if you're dealing with a normal soil, the conductivity is less than 4, the sodium adsorption ratio is less than 13, and the exchangeable sodium percentage is less than 15. So in that situation, no problems whatsoever. The second situation is when you're dealing with a saline soil. So in that situation, the conductivity of your soil extract exceeds this threshold of 4, but your sodium adsorption ratio and your exchangeable sodium percentage are still below 13 and 15 respectively. So you don't deal with a sodic situation. You're only dealing with a situation where the total amount of salts is relatively high. Okay, then the third situation is a sodic, when you're dealing with a sodic soil. In that situation, the total amount of salts is still relatively low. So the total amount of salts present in the soil is still below this threshold of 4. However, of the salts that are present, you exceed the sodium adsorption ratio as well as this exchangeable sodium percentage. So so even though the total salinity is relatively low, you still have a problem because your SAR and your ESP exceeds their thresholds. And then finally, the last situation you may encounter is that you're dealing with a saline sodic soil. So under those situations, both the total amount of salt in the soil is really high, but of the salts that are present in the soil, also a relatively large amount is present as sodium. And so, so in this situation, you have a combination of both the soil being saline, so the absolute amounts of salts is really high, but also you're dealing with a situation where the amount of sodium in the soil compared to other cations is really high. So, so hopefully that makes a little bit more sense. But again, the reason for showing this is that, you know, when you're talking about soil salinity, you really have to determine whether you're talking about total salts or whether you're talking about the relative proportion of sodium in your soil. And so here I show the same information in a slightly different way here. So here on the axis here, I show the total electric conductivity, so which is a measure of the total amount of salts that are present in the soil. And then here on this axis here, I show the sodium adsorption ratio and the exchangeable sodium percentage. So again, talking about total salinity, we use this number of 4 as the cutoff between non-saline and saline soils. And then here, as far as the sodicity goes, we use this cutoff of 13 for the sodium adsorption ratio or 15 for the exchangeable sodium percentage. So the soils here on the left are considered non-sodic. Then the soils considered on the right here are considered sodic. Then the soils here on the bottom are considered to be non-saline, and the soils here on the top are considered to be saline. So you can have these 4 situations. And so what is shown here also is when you look at the plants that, you know, the sensitivity of plants to the different salinity levels, for instance, here. So when you start getting salinity levels of above 2, then, you know, some sensitive plants may already start to get into trouble. But as the salinity levels go up, then, you know, plants might get more and more into trouble as far as dealing with these high salt concentrations. And when the salinity exceeds 12, it's only halophytic plants, so plants that are specifically adapted to these salty conditions that are able to grow. And this line here shows kind of the area, so all the situations within this range here, this is a situation where plants potentially can still grow, but outside of this range here, plants will have a very hard time to to be able to grow and to live. Okay, again, this is a lot of information, but it's kind of important, particularly later on when we start talking about how do you deal with salinity problems. Okay, so now having defined now what saline soils mean, the next step is why is soil salinity such a problem, particularly from a plant standpoint? And, oops, excuse me. So first of all, we're going to talk about saline soils and why is soil salinity a problem. And I put up this picture of a sponge here. And the reason for doing that is when I look at a soil, I basically look from a water standpoint, I look at a soil as being a sponge. So when you take a sponge, you put it under water, the sponge will fill up with water. You take the sponge out of the water, and some water will leave the sponge, but still a lot of water will stay behind in the sponge. And the soil, functions exactly the same. And so, but in order for the water to come out of a sponge after it drains, you need to squeeze the sponge. In other words, you need to apply a force to get water out of a sponge after it drained. And so from a plant perspective, even though soils can contain a lot of water, it takes work for a plant to get water out of the soil. And this is fine. Most plants are able to do that. But what happens if I add salt to a soil? And to understand that, I put up this picture here. And this is maybe a picture you may recognize from Thanksgiving dinner when things got a little rowdy and some people may have spilled a glass of wine on the white carpet. And I'm kind of make a joke about this, but it kind of illustrates the effect of salt on soil. So one way to get a red wine stain out of a white carpet is to add salt to the carpet, to pour salt on it. And so, because what salt does, salt attracts water. And so if you have a wine stain, you pour a lot of salt on the wine stain, you will see that the salt start to pull out the wine from the carpet. And then if you wait long enough and you use enough salt, then you can simply use a vacuum cleaner, vacuum up the salt, and hopefully your carpet will be back to being white again. And so, going back to that example that I gave as the soil being a sponge, so what happens if you add salt to this sponge, because the salt holds onto the water very tightly, basically you increase this sponge effect of the soil. And so from a plant standpoint, what happens is that it becomes harder and harder for plants to pull out water from the soil because the salt holds onto the water so tightly. So one of the main effects of high salinity in soils, is that plants have a much harder time getting water out of the soil. And so one of the common symptoms for plants growing in saline soils is that they suffer from water stress because the salt holds onto the water in the soil so tightly that the plants aren't able to get it anymore. And so again, sort of one of the first problems associated with high salt concentrations in the soil is that it can reduce the ability of plants to take up water. So plants can suffer from drought stress. There are two other effects associated with high salt concentrations that can be problematic for plants. One is that certain salts can be relatively toxic to plants. So sodium in high concentrations can be toxic. Boron in high concentrations can be toxic as well. So rather than have an effect on water uptake, it's the effect of high concentrations of specific salts can result in specific toxicities to plants, and as a result, growth will be affected. Another final secondary effect of high salt concentrations is that oftentimes when you're dealing with soils that have high salt concentrations, the soil pH of the soil is relatively high as well. And when the pH of a soil gets very high, certain nutrients may become deficient for plants or even toxic for plants. So pH of the soil is very important in terms of determining whether or not certain elements in the soil are present in very high or exceedingly low amounts. So depending on the elements, so for instance, at very high pH, certain micronutrients such as zinc or copper or metals like that, they become deficient because they're no longer available for the plants to take up anymore. So, and also phosphorus can become deficient at very high pH. So the pH effect associated with salinity can cause problems with nutrient toxicities and nutrient deficiencies as well. Okay, so that's about saline soils and the problems associated with that. So those are problems associated with simply high concentrations of salts. Now I wanted to talk about the specifics associated with sodic soils because they're somewhat different. And again, for that, to explain that, I have to go back to the chemistry a little bit and talk about clay minerals and how they behave in the soil. Okay, so going to sodic soils. Why is that a problem, and why are high concentrations of sodium a problem in the soil? And so in earlier talks in this workshop series, you may have heard about soil aggregation, for instance, and you may have heard that, you know, having aggregated soils is good for soils because if you have aggregated soils, then you have enough large pores to transmit water rapidly, but you also have small pores that allow for water retention. And so you want to have soils that have aggregates and that are in which the aggregates are relatively stable. One reason why you have aggregation in the soil, and I go back to that microscopy image that I showed earlier, you have these individual clay plates that are being attracted, that are kind of sticking to each other. And one of the reasons why clay plates stick to each other is if you have large amounts of ions present that carry two positive charges. And some of those ions include calcium and magnesium. So having relatively large amounts of calcium and magnesium in the soil causes individual clay plates to be attracted to each other relatively closely. And that's one main reason why you can have soils why soils can become aggregated, because the individual clay plates stick to each other in larger clumps. However, if you have relatively large amounts of sodium in the soil, and sodium only has one positive charge, then the attraction between individual clay plates will be a lot weaker. And so as a result of that, high amounts of sodium causes the individual clay plates to drift apart in a way. And as a result of that, aggregates in the soil will start to fall apart. And that's typically that can be a bad thing. And so whereas when I talk about saline soils, the effects are primarily because of problems associated with water uptake. In terms of sodic soils, the problems are primarily associated with a degradation of soil structure. And that can have impacts on water infiltration, for instance. And so that's shown here. So in this case, on the left here, you see a non-sodic soil. So you see a soil where you have nice aggregates. If water falls on top of the soil surface, it can move through these larger pores between the aggregates. And so, you have a healthy water flow in the soil. You can also have enough air entering the soil. So this is a really desirable situation. However, if you have a sodic soil, what can happen is that these individual aggregates start to fall apart. And you basically have a whole bunch of individual clay plates floating around in the soil. And what ends up happening is that because of the destruction of these aggregates, these clay plates, they essentially start to fill up these larger pores in the soil. And so the soil becomes the pores start to get clogged with these individual clay minerals. And as a result of that, water that falls on top of the soil surface won't infiltrate anymore, and you get standing water on top of the soil surface. And this can be a problem for water infiltration, but also for, as a result of that, air won't enter the soil anymore. So that can be a real challenge in terms of management, particularly when you try to irrigate an area. If you try to irrigate an area where the soil surface is completely sealed with these loose clay minerals, then water just won't enter the soil anymore. So that's a major problem. And so in practice, the way to how you can recognize that in the field, for instance, is shown here. So this is an image of a picture that I took. This is actually from near White Lake, near Cold Springs. And this kind of shows what a sodic soil might look like. And so when you look, for instance, here on the right, you see this white material. So it indicates that you have salt accumulation. But what you also see is that the top of the soil of these structure elements is completely sealed off. And that's because the individual clay minerals kind of started to drift apart and formed a coating on top of the soil surface here. And so water won't infiltrate right here. You still have, because this is a very heavy clay soil, you still have relatively large cracks between some of these structure elements. So water will still move into these larger cracks, but the surface here is completely sealed off by these individual clay particles that cover the soil surface. Then here on the left, you see another feature that may be associated with sodic soils and you see that the soil surface here is covered by this dark material. And so if you have high sodium concentrations in the soil, not only will clay minerals start to drift apart, but also organic matter that can clump together will start to drift apart. And so what you see here is a coating of organic materials, of small organic molecules that have drifted towards the soil surface and form a coating on top of the soil surface. And this can also prevent water infiltration. And some people may have heard of the term black alkali, and that's this feature here, where in sodic soils, you may have dispersed organic matter that moves to the soil surface and forms a dark coating on top of the soil surface. Okay, and another example here, what a sodic soil might look like is here, where deeper in the soil, you see these large structure elements, but you see this white material here, and you also see these rounded tops here. And this is also an indication of very high sodium concentrations, where because of the degradation of soil structure and the individual clay particles start to, or the soil aggregates start to fall apart, the edges of these structure elements become rounded off, and this can also cause problems. And so these individual clay particles start to fill up pores and cause problems with water infiltration. Okay, so just to summarize, I talked about soil salinity and soil sodicity. So again, the main effect of soil salinity, so high salt concentrations, is that plants suffer from water stress because they can't take up water very easily anymore, and also high specific ion concentrations can cause toxicity of certain ions. Soil sodicity can have a problem because it causes a degradation in soil structure, and as a result of that, water infiltration will be reduced, and that causes problems, particularly when you want to irrigate an area. Okay, so the next question, so now we know what salt problems can occur. How do I know if I have a salt problem? And that goes back to the way that we measure soil salinity. So earlier I explained the way that you measure soil salinity is using what's referred to as a saturated paste extract. So you take a certain amount of soil, you saturate it with water, you shake it, you let it sit, and then you extract the water, and then you measure the conductivity of the water, and then as you have more salts in this water, the conductivity goes up. And so this is a method that's been used since the 50s, and And so it's still very useful. And the way that, so it's been around for, close to 70 years. And this measure of soil salinity has been calibrated to plant responses. So, and what I mean by that is that for specific crops, these target salinity levels have been established. And the reason that this method is often used is that it essentially affects what happens in the soil when it's completely irrigated. And it's a simple method. You just need to take some soil, you shake it with water, and then you filter out or you extract the water from it. But the problem is it's relatively labor intensive. You have to take a manual sample, you have to extract it. And as a result of that, it takes quite a bit of time before you get your result, and it can be fairly costly. But what I wanted to mention is that there are other techniques available to measure soil salinity, and some people may have seen sensors that you stick in the ground and measure the salinity of the soil. And this can be very easy. This is an easy way to measure the salinity, but there is a problem associated with that. So when you measure the saturated paste, you measure the conductivity of only the water in the soil. However, if you stick a sensor in the ground, you not only measure the conductivity of the water in the soil, but you also measure the conductivity of any soil particles or any air that may be present in the soil. And so the conductivity of air, for instance, is much lower than that of water. And so when you measure the conductivity of the soil directly, you not only measure the amount of salts that are present in the water, but you also measure the conductivity of the minerals, of organic matter, the conductivity of any air pockets that are present in the soil. So the problem is when you measure the soil salinity this way, you can have different values depending on how wet or how dry the soil is, how much organic matter is present in the soil. So it's not exactly the right way to measure soil salinity. However, a lot of people unfortunately use this, and one of the reasons is it's very simple and it's fast. If you have a sensor, you stick it in the ground and you get an instantaneous reading. You can even hook up these sensors to data loggers and you can measure the salinity every hour. But a problem associated with this method is that it's very difficult to convert this measure to this saturated paste extract, which is kind of considered to be the standard measure to determine soil salinity. So be aware when you use these sensors that it doesn't always translate directly by these standard measures that are being used to determine whether or not you have a saline soil. Okay. So this is an example of what you might encounter if you take some soil samples and you send them off to the lab and what the type of results you might get. And I highlighted some numbers here in red. So again, these are a set of samples that I send off to to assess the soil salinity. Here you have this sodium adsorption ratio, the exchangeable sodium percentage, and the conductivity of the soil. So again, these two are measures of the sodicity, and this is a measure of the total salinity. So what you see here is for this sample, for instance, you see the sodium adsorption ratio and the exchangeable sodium percentage exceeding these threshold values of 13 and 15. So I'm dealing with a sodic soil here. However, the total salinity is still relatively low. So the soil is not saline, but it is sodic. The second sample here, you see that it has a very low sodium adsorption ratio and a low exchangeable sodium percentage, and also a low conductivity. So in this case, I have a soil sample where you really don't have any salinity problems or sodicity problems. And then finally, this sample, you have a very low sodium adsorption ratio and a low exchangeable sodium percentage. But you see that the conductivity starts to approach this value of 4. So in this case, I have to be careful that I may actually be dealing with some salt issues. And so here I have an example of a field survey I did. This is a field close to Honey Lake in California. And this area is about 1 mile by half a mile. And I went around and I took about 200 samples within this field to determine to see if I have a salinity and a sodicity problem. And so the blue colors indicate the areas where I really don't have any salinity issues, but you can see this red area here the salinity is around 5. So in this spot, I might deal with some salinity issues. Then here I have the sodium adsorption ratio. And so you can see here, these red colors, the sodicity or the sodium adsorption ratio exceeds this value of 13. So you can clearly see that here I may have some spots where I may have to deal with some sodicity issues. And again, this is an example of here where this spot, for instance, where the soil is sodic, but it's not saline. So again, it's important to make this distinction between salinity and sodicity. And also what this picture shows is, which is a relatively common feature, that when you look at salinity, it can be very spotty. So it's not like this entire field is saline. You only find this spot here where you might have some salinity problems, and also here where you have some spots here where you may have sodicity problems. So that's another challenge sometimes in terms of dealing with salinity issues. Okay, so I went around, took some measurements, and I figured out, okay, I may end up having to deal with saline or sodic soils. So what's the next step and what can I do about it? And so the reason talking a lot about soil salinity versus soil sodicity is that the way that you manage these soils really depends on what types of problems you're having. Do you simply have a saline soil, or are you also dealing with sodic soils? And whether you have one or the other problem really affects the way that you manage these soils. In general, in both situations, dealing with saline versus sodic soils or saline sodic soils, in both, the one common treatment in both situations is that you end up having to leach the soils, essentially to remove the salts from the rooting zone. But in the case of excess sodium, you also often have to add an extra amendment to the soil. And I'll talk about that in a little bit. So first of all, we're talking about saline soils. So the goal of treating a saline soil is to remove the salts from the rooting zone. And so the way to do that is simply adding water to the soil. And so if you irrigate a soil to promote plant growth, the idea would be to add extra water on top of what you need for the plants to allow for water movement below the rooting zone that will cause salts to be removed from the rooting zone deeper into the soil profile where it doesn't affect the plant roots anymore. And so one of the ways that we calculate how much water we need, that's also referred to as the leaching requirement. And I apologize, there's a little bit of math involved here, but I want to show this as an example of, in terms of what goes into determining how much water to add when you need to remediate a soil, when you want to get rid of salts. And so to calculate the leaching requirement, you need a couple of things. First of all, you need the salinity of the irrigation water that you're going to be using to leach the soil, but you also need the target salinity value. So, and different crops have different target salinity values. So certain crops can tolerate higher salinity levels than others. And so knowing the salinity of the irrigation water and knowing the target salinity of what you want to achieve, you can calculate the leaching requirement using this equation. Then the next step is, once you know the leaching requirements, how much water are you actually going to be needing to add? And so the leaching requirement, what it tells you is the excess amount of water that you need to add on top of what the plant needs to grow. And so the amount of water that you apply to the soil in millimeters per year you can then calculate that by, if you know the total annual crop water demands, and if you know the leaching requirements, that will allow you to calculate the total amount of water that you need to apply to the soil. And so here I gave a quick example of how you go about calculating that. So in this case, I know that the irrigation water has a salinity value of 1.2 decisiemens per meter, and I'm growing a crop that where the tolerance value is about 2.5 decisiemens per meter. So this is my target value. I also know that my crop needs about 800 millimeters per year of irrigation to grow. So first, what you do is calculate this leaching requirement. So you plug in these numbers into this first equation and you get this value of 0.1. So that means this value of 0.1 means that you need 10% extra water on top of what you add to sustain your plants. And so the total amount of water that you need to add to the soil, you then calculate using the second equation. So you know the plant demands, in this case, that's 800. I know my leaching requirement, which was 0.1, and you plug that into this equation. So in order to reach this target salinity level of 2.5 decisiemens per meter using irrigation water that has this salinity level, I need to add about 890 millimeters per year. And so that means that this extra 90 millimeters per year should be enough to remove any salts from the soil profile to achieve this salinity level. However, oftentimes it gets a little bit more complicated, and that the amount of water that you need to add is also a function of the soil texture and the depth of the soil that you want to be reclaimed. And so for instance, in a sandy soil, you typically need less water compared to a clay soil, and that's illustrated in this picture here. So if I want to reduce the salinity level by about 90% in the soil, then in this, this value here is the initial salinity level of my soil. I want to reduce it by 90%, so go down to this level. In a sandy soil, I need about 1 meter of water per 1 meter of soil that I want to reclaim. However, in a clay soil, I need to add about 2.5 meters of water per meter of soil that I want to reclaim. So the amount of water that I add to reclaim a soil not only depends on your target salinity, but also often depends on the soil texture. And so it gets a little bit more challenging. Okay, but this leaching treatment does work. So here's an example of a study that we did a couple of years ago where we had an area that was affected by salt. So you can see very high salinity levels of about 20 decisiemens per meter. So this area would be considered highly saline. And we kept irrigating this area for a few months. In this case, we used relatively low irrigation rates. But in this case, by the end of that period, you could see that the salinity was below 5 in most cases. So you can see that simply adding water, the salts were moved down the soil profile and the surface soil became non-saline. Okay, so that's for a saline soil. Now for sodic soils, it becomes a little bit more complicated because in addition to adding water, you also need to permanently want to get rid of any excess sodium. And in order to do that, you often need to add an amendment to the soil. And remember, when we talked about sodic soils, the big problem was that the soil structure was kind of destroyed. And so the goal is of treating a sodic soil is to restore the soil structure. So essentially get rid of these sodium ions and replace them with calcium ions, for instance, because if you have more calcium in the soil, that causes the individual clay minerals to stick together and essentially restore the soil aggregation. And to show how that works, I was going to show a quick video to explain this in more detail and show how this works in practice. So bear with me. Hopefully this will work here.
So today we're going to do a demonstration of dispersion and flocculation of soil. And we have here a sodic soil, a soil that's dominated by sodium, which causes the clay particles to push away from each other or disperse. So I'm going to put just about a teaspoon of this soil in each of these beakers. that just contain distilled water. Stir it up, and you'll see that it looks like chocolate milk. What's happening is the clay particles are dispersing, and they won't settle out because they're too small for gravity to pull them out of solution. Water molecules are moving around and will keep the clay particles suspended because the soil is dominated by sodium. If we put a different salt in, if we put calcium in, and here I have gypsum, which is calcium sulfate, and if I put some calcium sulfate in and mix it into the soil and water, then what's going to happen is the clay particles will clump together or flocculate. Now they'll be big enough that they'll act more like sand particles and they'll settle out. Okay, so here I'm putting half a teaspoon of gypsum in here, stirring it up, and then we'll watch this over the next half hour. And what we should see is that this one that just has soil will stay suspended. This one, which has soil and gypsum, is going to start to settle out. Okay, it's been about a half an hour since we stirred this up and let it settle. And you'll see that the one that just has water in it, this clay has stayed suspended. The clay particles are acting independently. They're dispersed. Where we've added calcium in the form of gypsum, that's allowed the clay particles to get close enough together to clump into aggregates or to flocculate. Now the aggregates are much bigger than clay. They act more like sand particles, and they've settled out. So if a farmer has a field of soil that has a lot of sodium in it, water won't be able to soak in, and plants won't be able to get the water. So what we typically do with a high sodium soil is to add gypsum. That's one of the treatments. Flocculate the soil, and then water will infiltrate and drain. We normally want a soil to be flocculated because the clumps in here can't get very close to each other. So there are big spaces between the clumps or the aggregates. So in a field of soil that's aggregated, water can infiltrate and drain through the soil, through those big aggregates. And when the soil drains, air can fill those pores between the aggregates and supply the plant roots with air and water. The dispersed soil will have very, very tiny pores. Water can't penetrate very easily. Water can't drain, and roots can't penetrate in through those tiny pores. So a dispersed soil is great for making a pond. So if we want to make a pond with clay, we could disperse the soil. That would be great. But if we want to grow plants in it, we want water to infiltrate and water to drain from the soil, then we want the soil to be aggregated.
Okay, so that hopefully showed what happens when you have sodic soil and when you add, and why you need an amendment to reclaim sodic soil. So again, you want to kind of re-aggregate the soil to allow water infiltration. So to kind of reiterate that, basically what you want to do is displace this exchangeable sodium that you have in the soil by adding calcium ions, because this calcium causes the soil to stick, or the individual clay particles to stick together again. So you have this exchangeable sodium, add calcium to the soil, the sodium will be replaced by calcium, and then the sodium will become part of the soil solution, and you can then leach that out. So they mentioned that, you know, gypsum is one of the main sources of calcium that is being added to the soil. A lot of soils that have salinity issues also have calcium carbonate. So you might think, well, why not simply use calcium carbonate? The problem is that under very high pH values associated with saline soils, calcium carbonate is not very soluble. So you don't have a lot of free calcium ions in the soil. So gypsum typically dissolves much easier. And so again, you have this exchangeable sodium, you add gypsum, the calcium replaces the sodium and you form sodium sulfate. And so sodium sulfate is highly soluble and can then easily be leached from the soil. Other materials can be used, such as calcium chloride or calcium oxide, but calcium chloride, you also add chlorine ions, which can be toxic to plants in large quantities. And calcium oxide is relatively expensive. So gypsum is kind of the amendment of choice in this case. However, if you have calcium carbonate in the soil, one treatment that some people do is adding sulfur or sulfuric acid to the soil. And what that does is essentially it lowers the pH. So sulfur is being oxidized to sulfate primarily through microbial organisms, and it reacts with water to form sulfuric acid essentially. And so what sulfuric acid does, it starts to react with calcium carbonate to form calcium sulfate, and the same process happens as what would happen if you simply add calcium sulfate. The problem is that when you simply add sulfur, because it's a microbial reaction, this reaction is relatively slow, so it takes a while for sulfuric acid to form and then to react with the calcium carbonate. And then sulfuric acid, you can add that directly to the soil, but it's a very strong acid, so it's not a lot of fun to deal with, and it's also relatively expensive. So that's why typically gypsum or calcium sulfate is being used. And so to demonstrate that this treatment actually works, so what this shows is a graph of the hydraulic conductivity, or the ease at which water transmits water, or the ease at which soil transmits water through the soil. Then you can see here some cases where you don't have gypsum added, and then the same soil following gypsum treatments. And so what you can see is that the conductivity of the soil increases as you add gypsum, which indicates that the soil structure is being restored and water moves more easily through the soil. Okay, I'm almost there. So just to summarize the reclamation strategies used for different salinity issues. So if you have simply a saline soil, so no sodic problems, the treatment is typically the easiest, and simply you add enough water to leach out any excess soils. When you have a sodic soil, which typically is the most challenging situation, so the total salinity is low, but you still have a lot of relatively large amount of sodium present, you need to add these soils with an amendment such as gypsum to remove any sodium, and then you follow that by leaching to remove any excess sodium from the soil. And then finally, saline sodic soils, the treatment is very similar to sodic soils. So you use a chemical amendment such as gypsum, and then you follow that up with a leaching treatment to remove any sodium. In all of these three cases, one of the main challenges you have is as soon as you stop these leaching treatments, if you don't permanently remove these salts from the soil, they have a chance to move back up to the surface again. So oftentimes you can't get away with just one treatment, and you kind of have to continue some of these treatments depending on the specific situation. Okay, then finally, just some parting slides is that in order for these reclamation strategies to be effective, first of all, you need to have good quality irrigation water, because you don't want to add any more additional salts to the water. You need, in case of sodic soils, you need to have appropriate chemical amendments. So you need to have access to gypsum. The soils need to be drained pretty well, because you want to remove those salts from the profile. And also so you need a place for these salts to go. So so if you don't want to pollute any surface water or things like that. And so in certain cases, soils may not be worth reclaiming because it may be too expensive. You may not be able to achieve a low enough salinity depending on the available irrigation water that you have, or the soil acidity might be so severe that you can't reclaim that anymore. And finally, you may not have access to good quality irrigation water, or you may have constraints on external sinks, so you may run into problems with polluting surface water. And so I'm coming to the end of the talk. I'm sorry I went a little bit over. I appreciate your attention. The only parting shot that I wanted to make is a shout out to my homeland, the Netherlands, where we also deal with salinity issues, but for a very different reason, where, you know, lands are being reclaimed from the ocean, where you have a lot of seawater. And so in those situations, you also need to get rid of salt from the soil, but obviously it's a very different situation as what you have here in the arid parts of the world. So again, my apologies for going a little over, but I thank you for your attention, and hopefully you've got some useful information out of this presentation.